Hey everyone, and welcome to my tool talk on optimizing away JavaScript obfuscation. These days, JavaScript is everywhere. It's inside your browser, and it's also on your desktop. From your chat apps, such as Slack, to even your coding IDEs, such as VS Code. But I'm not here to talk about the typical JavaScript apps that you're probably familiar with. Instead, I'm here to talk about JavaScript malware. Now, you might be thinking, is JavaScript malware even a big deal? And the answer is yes. JavaScript is a popular attack vector for getting inside a system through the browser. Now, this could be for installing crypto miners or as a first stage attack to leverage some kind of vulnerability in the browser and escape outside of the browser's sandbox. So if you're a malware analyst working in a cybersecurity operations center and you're given a piece of malware that looks like this, what do you do? Well, maybe the first thing that you do is apply some kind of beautification to undo the minified malware that we were just looking at. And if you did that, you would end up with something like this. Now, this is only a snippet of the previously minified malware that we were just looking at. It continues on for a few hundred lines, but even still, while this is a lot more readable than the previous screen, it's still not clear what exactly this malware is doing. So can we do better? And the answer is yes. Building on top of JavaScript static analysis frameworks such as SAFE out of KAIST in South Korea, I have built a tool, SAFE-DEOBS, that is useful for malware analysts in deobfuscating malware, JavaScript malware, to understand what a particular piece of malware is doing and making it more readable to the analyst. So this approach is described in more detail in my paper, but here is a high-level overview. SAFE-DEOBS takes in as input a piece of obfuscated malware. SAFE then raises this JavaScript to an abstract syntax tree to which we apply various pretty typical common compiler optimization techniques, and we keep applying these compiler optimizations to the AST until the AST stops changing, at which point we serialize the AST back out to readable JavaScript. So, what kind of compiler optimizations do we perform? Probably, if you're taking a compiler class, the first optimization that you learn about is constant folding. So here we have a single line of JavaScript from our previous example where we are comparing the type of a variable to some string that has been broken up into 3 substrings. So in SAFE, which is written in Scala, we can write concise, easily to understand rules to capture particular behaviors that we're interested in on the abstract syntax tree and manipulate the abstract syntax tree to simplify it and thus deobfuscate the malware in the process. So here we have a simple rule that matches on 2 string literals, stir1 and stir2, that are being concatenated together with the plus operator. And what this rule is saying, if we see this pattern on in the AST, then return a single string literal node with those 2 strings concatenated together. So visually, this process looks like this, where we have our 3 substrings recombined into their original string. And then if we serialize this back out to JavaScript, we get something that looks like this. So what other kind of compiler optimization techniques can we apply? You may have noticed in the original piece of beautified malware that there were many functions that only returned a single value. We can replace these function calls to these functions with this value that these functions return. This is function inlining. And again, in SAFE and in Scala, we can write these rules quite succinctly and nicely as follows. So this rule is saying that if a function body only contains a single statement and that statement is a return statement that is returning some literal expression, then we can replace that function call with that literal expression. Anything more complex than this then we say that we cannot inline and we just leave the function call as is. So if we apply this function inlining pass to the code that we just saw, then the call to this function gets replaced with its return value, which is null. And if we keep doing this to all the times that this function gets called, we can safely delete this function and we end up with code that looks like this on the right. Now you're probably guessing that from this you can apply further simplification techniques and further compiler optimizations to simplify this even further. So the first thing that we can do is reapply constant folding, and this if statement, the condition becomes a literal false. And we know just by looking at this code that anything inside this if branch will never execute because this condition can never be true. And so we can do dead code removal. This is essentially dead code, which we can delete, further simplifying the JavaScript and the amount of code that needs to be analyzed by the malware analyst. So we can keep applying these different compiler optimization passes to the AST, and at some point the AST will stop changing, and at that stage we can serialize the result out to JavaScript. And this is what we get. So we've taken a few hundred lines of JavaScript that we had at the beginning after we applied the Uglify.js beautifier to the minified malware, and we end up with about half a dozen lines of JavaScript shown here. Now if we look closer, we'll see that this is actually obfuscated PowerShell. So while we still have obfuscated code to deal with, the malware analyst is at least able to focus their attention on this new piece of code that may not have been readily visible in the original JavaScript malware sample. So in summary, applying compiler optimizations for the purpose of deobfuscation is probably not particularly novel. However, no such tooling really exists for JavaScript malware. And so in my opinion, my tool SAFE-DEOBS makes for a useful addition to a malware analyst toolset. This tool is available at the following GitHub link, and some questions to think about include what other techniques could be integrated to further improve SAFE-DEOBS, and how could it be combined with static analysis techniques to make the tool even more powerful. Thank you for listening to my talk.